Hello everyone, my name is Xiaoqing Deng, and I'm presenting my PhD topic on assessing the climate impact of formation flight in commercial aviation through network level path planning. As we know, and already been discussed by previous colleagues, the global warming is actually reaching or has reached 1.5 Celsius degrees set by the Paris Agreement for several times in the past years, and the average is reaching 1.5 Celsius degrees in the coming 4 years. So the mitigation method in near term is very urgent for us. So in aviation sector, we actually have three categories of mitigation measures. One is ATM operations and infrastructures. One is new aircraft technology, like the hydrogen aircraft Raul has discussed, and sustainable aviation fuel, as Omaru has discussed. Out of that, my topic is about formation flight, which is mimicking mimicking two birds or a bunch of birds flying in the air. We have formation flight flying in close proximity, and saving fuels and also saving climate and reducing climate impact. So formation flight as a near-term solution is balancing aviation manageability, operating cost, and climate impact. So when we look into the research for formation flight, the early stage was focusing on aerodynamic benefits analysis and research. And when we come to 1990s, commercial formation flight research came into place. And then it branches to path planning and also trajectory optimization after 2000s, or nearly 2010s. So the researchers first focused on very simple geometrical solutions to uncover hierarchical nature and the combinatorial nature of the problem. It's a deterministic model, and it's impossible to incorporate uncertainties. To overcome the difficulties, researchers look into trajectory optimization using optimal control applied to commercial formation flight. So it's a high-fidelity model. It can include uncertainties, and is minimizing fuel consumptions and CO2. So because of the high computational speed, high computational time, there hasn't been large-scale analysis being applied to this area of research. After that, climate impact assessment and mitigation potential has been assessed on both CO2 and non-CO2. Because of this limitation in the trajectory optimizations for the computational speed, is also not included for this kind of large-scale analysis. So the gap is very clear. Trajectory optimization lack the capability of adapt to large scale for climate impact. That's why it comes to my research goal, which is to develop a scalable formation flight planning framework to adapt climate-aware trajectory planning for large-scale analysis. I want to point out one thing here. We are actually taking one step back by saying that we are doing trajectory optimization, but we are trying to do first thing is trajectory planning. That means that we can obtain the most optimal solution, or we are obtaining suboptimal solutions. So that's in my scope of studies. So before tackling this problem, I want to introduce the two-level problem. So for formation flight planning problem from the literatures, it has been modeled as a two-level problem. The upper level is partner allocation problem that decides on how can flights be optimally paired or grouped for formation flight or solo flight. And then it takes the decision from the cost of the lower level, which is trajectory optimization results, and then to decide on who's going to be paired with who and fly with who. And for the lower level, we actually, as pointed in this figure, we have multiple lower levels. For each lower level, we calculate the trajectory optimization problem. This is a framework. And then we can see they are highly dependent on each other. And then there's also combinatorial factors, which I will dive deeper into for the next few slides. We propose a framework to deal with this problem is the bilevel optimal control framework, which I'm currently working on. And I came up to this idea before I came to the university and when I was having the interviews. And then I kind of developed it a little bit, but still there's a lot of work needs to be done. We simplify the problem to model each formation involving in two aircrafts as a pair. And then we solve it for multiple pairs, but is on a 2D horizontal plane. And we can see the upper level problem actually is a combinatorial optimization problem, and it involves the binary variables. And the total objective function is the total fuel consumptions for both solo flights, selected solo flights, and for selected formation flights. And then the lower level problems are actually trajectory optimizations where we're using surrogate model developed by one of my colleagues. And then we embed the functions for formation flight in it. This one is a little bit small in the size, by saying that the lateral distance between two aircrafts are greater than 10 wingspan for the safety reason and smaller than 20 wingspan for taking advantage of the aerodynamic benefit. So this lower level problem is very complicated, except for so we include flight dynamics, flight envelopes, and boundary conditions, and also this lateral distance constraint. So you can see combinatorial factors happens in the top because we are considering pairs and we're considering cost for each pair. And it also comes from the lower level because we have multiple lower levels, and the number of lower levels we have depends on the number of formations we have. So, and when we come to the bi-level optimal control framework, currently I'm working on is to reduce the scale of the lower level to have less lower level problems to solve. So I developed the formation suitability indicator. It's an idea to reduce combinatorial factors for the lower level problem. And then we deal with these two levels. But how to deal with these two levels? We actually normally would, in our engineering world, we solve it iteratively. But actually for bi-level optimization problem, we solve it by reformulating it to a single level problem, and then we solve it using nonlinear programming solvers. So this involves a reformulation, which is my work for my next half a year, and also to build a nonlinear solver, or maybe it ends up at the branch bound solver, depends on the linear relaxation if that's successful or not. And then we look into the formation suitability indicator. The goal of the formation suitability indicator actually is to create an indicator based only on solo in-flight information. We predict the formation fuel savings using the solo flight information as part of the work, and then we select the top pairs based on the percentage of the fuel savings. The method we use here in regression is the gradient boost and random forest. Why we use this simple method? Because we have, by obtaining the data we're having, the training data we have, we need to run all of the optimal control method, the optimal control solvers, but actually it's very time consuming. That's why we have to use this simple method for now. And then I do a training and testing on three experiments. And then the first experiment is for unseen flights, and second experiment is for unseen wind, and the third one is combining the unseen wind and unseen flight. And you can see the accuracy for the R-square actually is decreasing until 0.72. It's a little bit difficult to see, but I can read it out. And then we have each fold for each wind scenario, and you can see that it varies a lot for different wind scenarios. That's because the model is not very good of generalizing among all of the wind scenarios, and that's one of the limitations currently we have. And then the next part is that we implement this fuel saving predictions into a case study for a new data set. I'm going to skip this part and to the results. From after we implementing the fuel saving predictions, we can see that almost 92% of the fuel saving predicted are negative fuel savings, and only 8% of them are positive fuel savings for formation flight. And from the right chart, and you can see we have no threshold and 0-point threshold, which is we're eliminating 92% of the flights and then do an upper level calculation. And then we reach up to 10 tons of fuel savings for the whole 2 hours flight. And then if we move the threshold to more, like less conservative to 1.5% of fuel savings, which is we are removing 97% of flight selected, we can see a more like a significant drop on the fuel savings. That means that we need to set our threshold for this test at somewhere between 1% to 1.5% of fuel savings as the filter. And this is my current results for the formation stability indicator. And for my 4 years of PhD, I'm having 5 blocks of work to do. One is literature review, one is formation stability indicator, which I have done already. And then also I'm working on the bilevel optimal control framework, also on the reinforcement learning framework. Because the reinforcement learning framework that's why we define the problem as...
You have the 10 minutes already, so
okay.
You are about to finish.
But I'm going to move on. Yeah. This is the achievements, and I'm done. Thank you.